The title of the talk is Modeling and Visualization, and the study was conducted by myself, Kirot Budraj, and Rian van der Doel, also from the CSIR. So the objectives of this study is to demonstrate distributed processing, analytics, and the aggregation of geospatial vector sensor data, to implement distributed processing solutions such as Spark and GeoSpark into an existing streaming data infrastructure, or SDI, and finally, visualization of different data types from multiple sources or platforms in a graphical user interface, or GUI. So in order to reach our objectives, suitable input data is necessary. And for this, we simulated 2 data sets, and this was done due to a lack of available appropriate data, and we used Python to do this. In a previous phase, a streaming data infrastructure, or SDI, was put in place. The real-time GPS coordinates and temperature readings of some vehicle moving back and forth between 2 locations are simulated, and this was done to show the implementation of near real-time sensor readings into the SDI. For the next data set that we simulated, the relative position of 5 individuals or workers walking in different directions through a tunnel with a narrowing in the middle was simulated. And this was done to demonstrate the aggregation of different data streams at near real-time streaming analytics. And finally, the last data set was not simulated, but obtained from a different platform, a data science platform, where a geo event or a seismic event was predicted for a mine, and a model was run using machine learning to predict if the event will occur or not. All these data streams and data sets were sent to the streaming data infrastructure using Kafka. So for the streaming analytics part, the relative worker location data consists of 5 data streams that are aggregated before analytics can be conducted. We calculate the relative distance between individual pairs at different times in order to determine the distance between them. If the distance is less than 1.5 meters, then an proximity event is recorded. As you can see in the image here, we compare the different individuals, and then in the first table here, you can see person 1 and person 2 were 0.97 meters apart, which of course is less than 1.5. And so the time of this occurrence, as well as the ID of the individuals and the distance, are recorded and saved. So in order to be able to use this data, it must be saved into some type of database. All raw sensor data is considered Internet of Things, and so saved to a Frost IoT database. At the top, you can see observations and location, which is data from the first GPS and temperature dataset are saved into a Frost database. And below, you can see the analytics and results from the machine learning saved into a Django database. And this is just kept separate because it's different types of data. So finally, the different data sets must be visualized in some type of graphical user interface. We decided on Dash, which is a Python application. So the first data set, GPS and temperature data, is in the first tab here named Temperature Sensors. So as you can see, the temperature data is recorded in the graph, and the orange or red dot is the current temperature, and it's updating in real time. The corresponding GPS location of the vehicle on which the sensor is mounted is shown in the map next to the graph. Below, the temperature and positional data is aggregated, and the last 10 readings is shown in the table. So next, the worker's relative positional data is shown in the tab named Contact Sensors. So here, the raw sensor data of the relative positions of the workers is shown in the graph, with once again the big dot showing the current location, and the results from the analytics is shown in the table. the graph can be moved back in time to show snapshots at previous instances by using the slider, and the table, which contains the time that the event was recorded as well as the individuals involved and their relative distance from each other, can be filtered using the controls below. Finally, the prediction results from the data science platform is shown in the third tab. When a geo event is predicted, a 1 indicates that an event will occur, and a 0 indicates that the probability of an event occurring is very low. So in this figure below, you will see there's zeros and ones showing the absence or the presence of a seismic event or that will occur. And in the table next to it is the time that the prediction took place, some parameters used in the prediction, such as maximum energy, and then the probability of the event occurring. So here in this case for event 571, the probability of a hazardous event is 0.59%, or in this 59%. So if we look at this, there's a lot of hazardous events, which is not good for a mine. But this is because even though the data was measured at an actual mine in Poland, it's in a static database and the data is randomized. It's also sped up so that such a prediction will not take place at this frequency, but significantly slower, perhaps once or twice a shift. And all this has now sped up and showing these hazardous events due to just the sped up for demonstrative purposes. In the case where a hazardous event is predicted, the warning light at the top will show red, and if no hazardous or seismic event is predicted, the light will be green. So in conclusion, near real-time and efficient analysis and processing of rapidly streaming data coming in from multiple sources was conducted and implemented in the SDI. Due to the versatility of Dash, it was possible to easily upscale the user interface to incorporate the visualization of different data types, such as near real-time streaming and sensor readings, streaming analytics, and machine learning results. Thank you.